Okay, so in this one, we have a woman standing on the ground watching a jet through a telescope. It's approaching at a speed of 10 miles per minute and an altitude of 7 miles. We want to figure out how fast the angle of the telescope is changing when the horizontal distance from the jet to the woman is 24 miles, and then also when the jet is directly above. Okay, so let's say here's our jet. There's going to be a really fancy looking, there it is, jet. Okay, and she's looking up at this thing, and we know, I'm going to say her height is close enough to negligible in this situation. My picture is very not to scale. But we know that the plane is approaching at an altitude of 7 miles. I don't see anything that implies that that's changing, so I'm just going to fix that. And it's approaching at a speed of 10 miles per minute. 10 miles per minute. So let's give that a name, dx/dt, I guess. And then we need to think about what x represents. If dx/dt represents how fast the plane is moving, then x better represent some distance. The fixed point I see in this problem is her, so I'm going to go ahead and make this my x. And the only thing that I have to be careful about based on that is that then x is decreasing, so it's negative. It's decreasing by 10 miles per minute. Okay, we want to know at what rate the angle of the telescope is changing. So here, let me actually pretend this was closed off. So I'm going to call that theta. The angle of the telescope, that's a little vague, but pick an angle. You could do it from vertical, I suppose, if you wanted to, but this seems like the easy one. From ground level, how high up is she pointing? Angle of elevation. When the horizontal distance. Okay, so we want to find d theta dt when x is equal to 24 miles. So I need a formula that relates theta and x. Those are the two variables that I've had to introduce. And I would be totally happy for the 7 to be in the mix as well because that's fixed. So a formula that relates theta to 7, which is opposite, and x, which is adjacent, would be tangent. So let's say that tangent of theta is equal to 7 over x. And here again you have a choice. We're looking for d theta dt, so sometimes it makes life a little easier if you first solve for theta. Sometimes it makes life a little harder, so feel free to play around. I'm going to go ahead and solve for theta because I haven't done that yet. So it is legal to say, well then theta is equal to the inverse tangent of 7 over x. And that kind of turns this into more of a chain rule problem and less of a related rates problem, although we still have the hidden t, so there is still some related rates. Okay, so based on that, I can say that d theta dt is equal to the derivative of inverse tangent, which is 1 over 1 plus 7 over x squared. And then chain rule says I need to multiply by the derivative of 7 over x. Remember that 7 over x is the same as 7x to the negative 1. So this is going to be, derivative is going to be negative 7x to the negative 2, which looks like that. So, do I like this? I actually do like this. This worked out really well. We were looking for d theta dt. Oh my goodness, I almost forgot something. I did one chain rule, but there's another. Okay, so we took the derivative of the inverse tangent, that's this first part. We took the derivative of the 7 over x, that's the second part, but we never took the derivative of x. So there should be a dx dt. Shame on me. Okay, so we know that x is 24. And we know that dx dt is negative 10. I think I have to break my avoiding the phone calculator thing off here because there's no way that I think I'm doing that in my head nicely. Well, maybe. I'm not going to mess with it. Okay, so calculator. Okay. I don't even know if if this will show nicely for you. But we have, I'm going to try and do a little of this in my head. We have, maybe I'm not, 1 over 1 plus 7 over 24 squared. Where is my exponent? Is it this one? Nope. Oh, there it is. Squared. Times a negative 7 over 24 squared times a negative 10. Okay, so I get this, 0.112. So that is supposed to be how fast theta is changing with respect to time. So that, by default, theta should be in radians, unless you at some point plugged a trig function into your calculator and told your calculator to use degrees. This should be radians. And you don't actually have to write radians, but sometimes it makes it easier to make sense. Radians per minute. So if the plane is approaching at a rate of, 10 miles per minute, then the angle of the telescope has to increase by 0.112 radians per minute. Okay, so one thing I want to point out here is that if we hadn't done this rearranging, when we took the derivative, we'd get a secant squared theta d theta dt, and that secant squared theta isn't just going to go away, so we'd need to know theta in order to plug in enough information to find d theta dt. That does not stop us. All we'd have to do is go back and say, okay, well, if this is 24 and this is 7, I could take the inverse tangent of 7 over 24 and get a theta value for that specific time, and then you'd plug it in. So it would be kind of similar to when we did the Pythagorean theorem problem. What else are we supposed to do? How fast is the jet moving when it's directly above her? So this is second part. What about when x equals 0? And when x equals 0, oh, we can't do it. I don't know what I was looking for when I wrote that part of the question. Maybe just for you to notice this, but x equals 0 makes this thing definitely look undefined to me. So we're not allowed to use this tangent function for x equals 0. All right, thanks for watching.